Okay. If you guys continue taking chemistry with me over the next year and a half, I'm going to say this to you more than once. I'm going to apologize and say I lied to you. Well, I didn't like full-on lie, but I told you a half-truth. And I do this a lot in chemistry because chemistry is so big and overwhelming sometimes that to make things simple, a really complicated topic, when you're maybe not ready to learn all of it yet, I tell you one thing to kind of give you an idea in your head to go off of, but then later I'm going to come back to it and maybe extrapolate on it more. Does that make sense? That's what I'm going to do today. Today I want to talk about strong versus weak. And I've mentioned these words to you in the past, mainly because I don't want you to use the word strong instead of the word concentrated. And I don't want you to use the word weak in place of dilute. So in the past I told you if something is strong, it conducts. And if something is weak, it doesn't conduct. That's like a half-truth. Sorry. I kind of do this though to try to make things not so complicated right off the bat. Strength is not purely whether it conducts or not. It actually works kind of backwards. So I'm just going to read off my slide here. Previously we have learned that strength is determined by how well a solution conducts electricity. It's probably better the other way around actually. It's accurate to say that a solution conducts because it's strong. Maybe that sounds weird because it doesn't mean the same thing. Strength does not happen because it conducts. Things conduct because solutions are considered strong. Does that make sense? All right, let me try some images here. A strong acid or anything that's considered to be strong, it means that it ionizes to a large extent. Okay. What does ionizing mean? It breaks up into positives and negatives. If something ionizes, it means it was molecular. Do molecular things do they actually have anions and cations and I shouldn't say that. Do they have metals and nonmetals? I'd say no. Molecular things should not really break apart. So when they do, often it's rare. Like they're not supposed to do this under normal circumstances. Some things, they will break apart all the time. Like say HCl. See how these HCl bonds right here? Pretty much all of them were broken. I might say that like 100% of these bonds were ionized. The more that things break apart, the stronger they are. In chemistry, strength is actually not a measure of conductivity. Strength is a measure of your ability to break apart. Does that make sense? I'm going to use the analogy of couples a lot today because you can almost consider this to be like a boy and a girl in a relationship, for example, and then they break apart. So in the chemistry sense of the word, if someone is strong, they like to break up. Okay. So HCl in this example is very strong. All of these couples here have split apart. That's what makes them strong. As a side effect of being strong, you see how there's now a whole bunch of positive and negative charges? Now it can conduct electricity. Does that make sense? So because everything breaks apart into pieces, then it conducts electricity. So when I told you that strong means that it conducts electricity, yes, I told you like a partial truth, but I want to elaborate on that. Often what we'll do is we'll write a percentage sign above an arrow, implying that this is how much of this stuff here actually converts to products. I use a lot of photos today. Here's an example of like, say, a strong acid. Why is it strong? Well, not because it conducts. It is going to conduct, by the way, but that's not why it's strong. The reason we call it strong is because you see how all of these molecules here used to be in groups of 2 all attached together? Almost all of them have ionized and broken apart into like white and red and white and red and white and red. Mm-hmm. So almost everybody has broken up and split apart. Therefore, that's what we call strong. The ability to break apart makes you strong. Okay. Whereas someone who is weak, I'm going to close that window. Give me a second. Someone who is weak, in terms of, specifically we'll talk about acids, weak things do not break apart. They don't have the capacity to break those bonds. So there's like a bond inside this molecule here, it didn't break. And there's a bond inside this molecule here, it also didn't break. These guys right here, they did break. And maybe these guys here, they did break. But you see how like here, everybody broke apart? And here, some of them did. That's what strength is. Which solution will conduct electricity? Well, this one right here, you guys remember those like conductivity meters you used on Monday? This one right here should probably be a 10 out of 10. It should conduct really well. Whereas this one right here, it'll conduct like a little bit. Maybe it'd be like a 4 out of 10. Did you have a couple of them where they kind of conducted a little bit? Right, that's what this one would be. Does that make sense? So going back to my initial premise, strength does not mean it conducts. Strength means that it can break apart, and as a side effect, it conducts. So that's why I have to apologize. I told you a partial truth, but hopefully that makes sense why I told you a partial truth, because I didn't feel like maybe we were ready to talk about this language yet until we finished most of the unit. So most of what I have here now are just diagrams. This guy is strong because there's all sorts of pluses and minuses everywhere. Everything is ionized. Here it's weak because a lot of these HFs are still stuck together. Make sense? In terms of like general, like how you can tell whether it's strong or weak, most things are either well above 99%. Like say this guy right here. All of these are water molecules right here. All of these water molecules have been able to pull all of these apart into pluses and minuses. And so like this guy and this guy and this guy have all been ripped apart. Here, this guy's a weak acid. And see how this molecule is still kind of stuck together? It hasn't been ripped apart yet. So, anyways, here's my point. More than 99% usually means it's strong. Pretty much everything else, if it's not above 99%, is usually less than 50 actually. Typically it falls into that category. I don't know of many things that are either like 60 or 70 or 80. It's almost like it always happens, or it's less than half. That seems to be the breakdown of things. I'm going to skip ahead here. How will you be able to tell whether something's strong or weak? We have a table in your data booklet. Do you guys remember me talking about this table at some point? See if you can find this one in your data booklet. It's a table you have to turn your data booklet like up and down for. It's like the second last page maybe? Page 8 and 9? Yeah, that's the one. This is a ranking. We're going to work with this table a lot more in grade 12. Again, I'm going to tell you a lot of partial truths, and then we'll focus on this in grade 12 a lot more. But here's what you guys need to know. This is a ranking of strength. Perchloric acid will split apart all the time. So perchloric acid will split up into H plus and ClO4 minus. Often what they do in this table then is they don't bother writing the H plus because everything is going to split off an H plus. So then what they do is they tell you, well, this is what the other half is going to be. So like HI will always split up into H plus and I minus. H plus, Br minus. H plus, Cl minus. H plus, HSO4 minus. H plus, NO3 minus. These 6 right here above the hydronium line are considered strong. They always break apart. So if I use the analogy of like a couple, hydrogen and iodide are getting a divorce. Always. Hydrogen and bromine breaking up, Splitsville. Whereas these guys down here, they will split up, but like sometimes. So like maybe half of them will, half of them won't. Or maybe like 5 of them will and 95 of them won't. So like for example, this guy right here might be like say about 50%. They break up. This one right here might be about 49%. 48%. Yeah, these guys right here are typically less than 50. Now, I don't actually know the exact percentage numbers, but it decreases as you go down the list. What is the lowest thing listed on there? Like, I don't actually have the whole table listed, but what is the last one way down at the bottom? Water. Does water have the ability to break up into OH negative and H plus? Yes, it does. We talked about this last day. But it does come back together too, by the way. But how often does it do this? Do you guys remember the number? 2 times in a billion. So do water molecules have the ability to split up and get a divorce, so to speak? Yep. But no, water is actually, I mean, in terms of strength or weak, water is actually very weak, but by weak, I mean it's actually good at sticking together. It's not going to separate into pieces. Yeah.
What is the hydronium for
The hydronium? This one right here?
Yeah.
This one's more just like a reference. It's not actually like on the line so much, I guess. It's just this is the break-even point between like the top 6 and the bottom whatever. Does that make sense? Like it's not actually really it doesn't really belong here with the rest of them, I think. Does that make sense?
Yeah.
So I guess what you could suggest is the hydronium has the ability to rip off a hydrogen and become H2O plus, right? Which is kind of what I've been describing all year, is that H plus really attaches itself to a water molecule to kind of like find some solidarity there. So it is possible for this H plus to rip off of it, I guess. It's probably just best just to, this line is just to indicate like where the difference is between all of these guys, very large, implying they do this all the time, and these guys down here, which are progressively getting weaker until you get down to like 2 parts per billion for water. Does that work? That's basically it. It's a theory lesson I have today. So let me just cover the rest of my slides. Weak things then do not ionize very well. Do they ionize occasionally? Sure, but not all the time. So here's some properties. Usually they don't conduct quite as well. They react a lot slower. And they usually have higher pHs. Why would it have a higher pH? Here's a weak acid. Here's a strong acid. How do you calculate a pH? What's the formula for pH? pH is equal to the negative log of H3O plus. Basically what happens is the more H3O pluses you have, the lower the pH, because it means there's more of them. Does that make sense? This guy right here should have a very low pH because there are lots of hydroniums. It has a very high concentration of hydroniums. Right here, are there some H pluses? Sure. Could there be more? There could be more. I mean, I'd love to rip this hydrogen off of that guy, and I'd love to rip this hydrogen off of that guy, but apparently it's just not strong enough to do so. So are there H pluses? Sure, but there's not as much. So that means this will have a higher pH because there's less H pluses. Either way though, the pH will be less than 7. Like this might be a pH of say like 1, a very strong acid. And this might be a pH of say 4. Is there still a lot of hydroniums there? Sure, there's a reasonable amount of hydroniums or H pluses, but there's not nearly as many as the guy next door. Because here, everybody breaks apart, and here, some of them break apart. Does that make sense? Cool. Oh, I should point this out here. Strong acids then are less safe to handle. Basically, if you have lower concentrations of hydroniums, they're safer. So long story short, the strong acids are more dangerous than the weak acids. We should talk about bases as well. Bases are typically ionic compounds. Do ionic compounds ionize? They dissociate, and that works a little differently. Ionic things are made of metals and nonmetals, and they almost always break apart very, very easily. Ionic bonds are actually very weak bonds sometimes because all you have to do is put an ionic bond in water, and it breaks apart. Like say salt. You put salt in water, it dissolves really easily. So ionic bonds are actually not as strong as other bonds can be. Hello. So strong bases typically dissociate 99% of the time, and weak bases are usually less than 50%, just the same way. Talked about this table. I'm going to skip ahead to this last slide here. Yeah, let's go to the last slide, and then I'll go back to the second last slide. Okay. One of the things that I asked you guys to do in your lab was on paper, tell me whether something is like an acid or a base. Like for example, this guy right here, H3PO4. If I take H3PO4, my first question would be, is it ionic or covalent? You'd say it's covalent or molecular, whatever you want to call it. So molecular things need to ionize, so I'm going to add it to water. If I add it to water, I could take one of this guy's hydrogens and add it to water to make the H3O plus. Therefore, he's an acid. That makes sense. Is H2PO4 a thing? Hopefully by now you're starting to recognize that, yeah, it is. So this is totally a good reason why this guy is an acid. There are some acids then that can react multiple times. This guy right here could then come down and he could react with water. You see how this guy has two H's left over? I could peel another H over to a water, make more hydronium, and now it becomes just HPO4 2 minus. Is this a thing? It is actually. You can even do this a third time. This guy could then go down here, lose its last hydrogen to water, and become PO4 3 minus. Is PO4 3 minus a thing? Yes, it is. Why can't it react anymore? Why are we done? It's out of hydrogens. Yeah. Basically, the idea is if it's like H3 something, or H2 something, or H1 something, sometimes it can react multiple times even. Yeah.
So the two top ones are acid, and what is the bottom one?
Still an acid, because it's still proved an acid.
Oh.
So like, this acid made acid in something else, and this made even more acid, and this made even more acid.
And you said that's because of the H3O?
Yeah, this is what makes it an acid. Okay. I want to reference that compared to a previous example. Here's HCl. So again, is HCl ionic or covalent? You'd say, well, it's not
Mr. Petluck,
ionic,
can you please call
because hydrogen's not a
100?
metal.
Mr. Petluck,
So it's
please
a
call
covalent
100.
bond. So add it to water, make it H3O plus and Cl minus. Can I react the Cl minus a second time and make it rip off another hydrogen?
No.
Not really. Here is one thing you could try to do, but I'm not going to expect this. You could try to take the Cl minus, react it with water. It would try to make HCl and OH negative. And then you could take the HCl and react it with water to make H3O plus and Cl negative. And then you could take that Cl negative and react it with water to make HCl and OH negative. And I could keep doing this for forever, because I'm kind of getting into a loop if you're noticing this. And so even though all of these equations are hypothetically possible and I could just keep going for forever, if you start getting into a loop, we usually stop writing these ones and say this is getting kind of ridiculous. I've proven though that somehow I get base and then acid and then base and then acid. Then maybe that seems contradictory, because it's like, well, no, this right here is an acid. How did you all of a sudden make it a base and then make it an acid and make it a base? What's about water? Doesn't water have the ability to break apart into acid and base? But then what does it do? Does it just stay there? Well, no, it reforms back into water again. And often we draw these arrows right here as like double-sided arrows, indicating that things will split apart, and then they'll come back together. Then they'll split apart and come back together. And it's that analogy of like a bad teenage TV show where like the couple, they get together, they break apart, they get together, they break apart. And it's constantly doing that. Does that make sense? So like this is a valid expression because my Cl ripped the hydrogen over here, leaving OH, but then the HCl then rips the hydrogen back the other way. So I mean, it kind of gets ridiculous to keep trying to write this. So I just wanted to point out, if you ever get stuck in that loop, you should stop. So last thing I want to talk about then, if you have multiple reactions, the ionization percentage always goes down, we've discovered. So like, let's say these guys ionize at, say, is H3OP strong or weak, by the way? Someone have a table nearby? H3OP is not one of the strong ones. So let's say this guy ionizes at 47%. This next one will ionize at a lower rate. So this one might only ionize at, say, 23%. And then this one might only ionize at 11%. I guarantee you, like this is what we've discovered, each progressive reaction you look at, the percentage for how much they split apart is always less. It never gets better, if that makes sense. So I don't actually care what these numbers are. That's not really relevant to us in this year here. I just want you guys to know the numbers always decrease. That's what I have written right here. That's it. I'm done. That's a quarter of the year. We finished 1 out of 4 units.